All right, I see that most of the people are here that we expected. So we'll start formally. Like I said, my name is Becky Eldridge. I work here at Walker Consultants out of the LA office, and I work in marketing. It is my great pleasure to work with a great number of talented folks here at Walker. The topic today is the root cause, the value of forensics engineering. And if we can go ahead and flip to our bios, I'll give you a quick intro to our speakers, who you should be able to see on the screen. Al Bustamante and Charles Hammond will be leading you through today's session. I will come in at the beginning and then at the end, where we'll have a Q&A session. So feel free to note any questions at all throughout the session in the questions panel, and we'll address them all at the end. So to introduce each of these gentlemen, Al is an expert with more than 18 years of experience in the evaluation, non-destructive testing, and design repairs of a variety of structural, architectural, and material distress-related projects. His experience includes non-destructive testing of concrete structures, computer modeling and analysis of steel and masonry structures, design of repairs for steel structures, and building envelope assessments. Charles Hammond has more than 14 years of experience providing structural engineering services both domestically and abroad. Charles' design and forensic experience has included various structure types such as stadiums, medical facility, high-rise buildings, residential buildings, pavements, retaining walls, marine structures, industrial structures, and parking structures. The structures have utilized a variety of materials, including structural steel, wood, soil, and concrete. Charles's diverse international and domestic background has included restoration projects, new design projects, forensics investigation, and litigation work, among others. Services provided on these projects include structural analysis, construction administration, repair design, load testing, non-destructive testing, failure investigation, peer review, identification of construction and design defects, and expert witness services. Thank you all for joining us. And now I will turn it over to Al, who will walk us through the first part of the webinar.
Okay, thank you, Becky, for the introduction. And I'd like to thank everyone for taking the time to join us here today. I know everybody's busy, so we're going to get right to it. So what we have today is a half an hour to 35-minute presentation, and then we're going to leave some time for questions and answers. As Becky pointed out, the title is The Root Cause Forensics. So the outline of the presentation, we basically have three topics that we want to cover. First of all, we're going to go through an introduction of some terms that we will be using throughout the presentation. Then I'm going to talk about the investigation process. And then after that, I will turn it over to Charles Hammond, who will cover the case studies. So the first part, the introduction, we want to talk about some key terms that is basically the focus of this presentation. The first one is an acronym ASPS, which stands for Architectural and Structural Problem Solving. This is basically an acronym that I came up with to try to describe this type of services, which basically means solving problems or providing solutions essentially for the built environment, whether we're dealing with the parking structure, a building, a monument, a bridge, whatever the case might be. That's what this field is about. And it could involve a legal case, it could involve a claim, or it could involve a project where there is a restoration component. So we're going to cover the full spectrum of what ASPS is about. The other two concepts that we're going to talk about are structural significance, and what that means is basically the structural significance of the distress condition that we encounter with these architectural structural features. And also we're going to talk about the difference between two concepts that are very important for forensic engineering, which is defect and deficiency. And this is what we're going to focus on are the technical terms, more from a structural engineering standpoint, more so than a legal term. I know legally construction defect has a certain terminology. What we're talking about here is the difference between those two terms when it comes to the technical aspect of it, and ultimately how all these concepts affect the bottom line on all these projects and all these issues, which is basically the cost. So the first item is, as I mentioned, ASPS. So when we talk about forensics, we're not talking about just the legal type work. I know typically forensics is kind of associated with litigation type work, but it's not necessarily the case. In some cases, we might be dealing with just a restoration type scenario. So that's the full spectrum. And we'll show some specific case studies, and I'll talk about a few examples to kind of illustrate that concept. And really, one of the first is how much do I know about the problem? And the reason is because depending on how much I know about the particular problem, the more accurate that solution that we develop can be. And the relevance of that is that the less I know about the structure or the problem at hand, the more conservative I will have to be with the assessment and the solution provided, which means that the cost is higher. So there's a direct relationship between the conservatism that is used to provide a solution versus the cost. So this is why it is important to perform a thorough forensic investigation to allow the forensic engineer to really understand the problem, kind of dive into the details, know the root cause of that problem, so that ultimately the cost can be minimized, whether it's the cost of a claim, if we're trying to work on conflict resolution type issues, or if we're trying to help an owner minimize the cost of maintaining the structure and kind of extending the service life of the structure. So let me illustrate that with an actual example, real life example. So what you see here on the screen are a couple of photographs or a precast concrete column in a parking garage. And as you can see, there's a lot of cracking. So this thing, I mean, it looks like a horror movie. I mean, the client was very concerned when they called me and they showed me this cracking. They said, well, you know, it's the sky falling. You know, this looks like a big problem. And they actually had a recommendation from a consultant to replace the columns, which was in the order of several $1 million. So they asked me to take a look at it and give my opinion. So essentially, in this type of the projects, this is where the forensic engineering come into play, where we can take a look at it further than just visually to really understand the problem. So the first thing that we do is basically look at the entire elevation, big picture, where the cracks are located, you know, how closely spaced they are, and to really understand kind of if there's any pattern in the cracking. And this figure that you see here on the screen are basically the elevations of these precast concrete columns, kind of showing the location where the cracks are. And as you can see, there is a little bit of pattern. There's some of those cracking is kind of close to some of the joints. The next step is we look at the reinforcement. So we use a technique called ground penetrated radar testing, which is a non-destructive evaluation technique to estimate the location and spacing of steel reinforcement. So what you see here in the photograph is on the right side, you see the column or the face of that column. And on the left, you see the output from the ground penetrated radar testing machine. And the red lines, the dotted lines, are the location of the steel reinforcement. So there's a lot of steel reinforcement intersecting these cracks. So that was good news for the owner, because basically that means that there is plenty of steel reinforcement maintaining the cracks tight and also maintaining the integrity of the concrete. The other thing, I want to direct your attention here to this yellow rectangle or yellow square, and that's the area where the load is being transferred from the floor deck to the columns. And that area basically had no cracking. It was in really good shape, which is also another good news for the owner. So that's one step of the process in this forensic investigation. The other thing that we did is we actually took core samples from the columns themselves. So this particular photograph shows a core sample taken at a crack location. So the photograph on the left, what you see is the left side of that photo is the outside of the column, where you can see the crack is a little bit wider, and then it kind of narrows as it gets to the middle. And this is also good news because the strength of this concrete column is really in the center of the columns were inside what's called the cage, the steel reinforcement cage. And really what's on the outside of the steel reinforcement is more for durability purposes and also for fire code type purposes. So this is also good news for the owner. So as you can see, we're kind of starting to put the pieces of the puzzle together. We also took some concrete core samples at a location where there is no cracking, and this is called a control sample. And the reason for that is to compare to the location where there is distress and see if there's any differences. So what we do from here is we take those samples, send it to a lab where a petrographer, who is a scientist that basically looks at concrete under a microscope, and they can tell us different things. So we want to evaluate also the material component just to see, what's the significance of these cracks. So what the first thing they told us is, and what you see here on the screen is basically a vertical cross section on that core. You can see where the crack is, shown by the blue arrows. And then you see this yellow line, and the top of that yellow line is called a carbonated layer. So basically what that means is that the alkalinity that is part of the concrete has kind of run its course. And the alkalinity is what the concrete relies to provide protection for the steel reinforcement. So we want the concrete to have alkalinity. And for the most part, so what you see from the yellow line below is that kind of pinkish, reddish color. And that is telling us that area of the concrete, that portion of the concrete, it has alkalinity, which is good. So essentially, what this is telling us is that we have good concrete in general in terms of the alkaline content to provide protection for the steel reinforcement. So all these are very good news so far. The petrographer also looked at a couple of with a much higher magnification, look at very thin sections of the concrete cores. And what they told us is that there's a couple of expansion mechanisms that are occurring from within the hardened concrete. And in this figure here, what you see is a mechanism called delayed ettringite formation, or DEF. And basically what that is an expansion mechanism that occurs in the paste of the concrete. And there's two things that need to happen for that mechanism to occur. There needs to be the ettringites, which is part of the cement clinker, and there's nothing you can do about it. It's just part of the concrete. And the other one is moisture. So which means if you don't have moisture present, you don't have the expansion mechanism. So that is good news for the owner because that moisture could be controlled. And in terms of relative humidity, we're talking about 70% or so. So we can keep that relative humidity down. We can minimize this mechanism. And the same thing, this is another figure that shows another expansion mechanism. This particular one occurs from within the aggregate. So you can see the two yellow arrows here kind of pointing at that dark line. That is that expansion mechanism that occurs from within the aggregate that's called alkali silica reaction, or ASR. And this mechanism also needs the moisture in order to react. So after knowing all this, basically what we found is that the cracking mechanism really doesn't have any structural relevance. The columns structurally were sound, and really the cracking occurred kind of on the outside face of the columns. And the importance of that is that a repair only involved basically sealing the cracks and applying some surface penetrating sealer to essentially control the amount of moisture that gets into the concrete. And if there is no moisture, or the relative humidity is below 70, then you don't have the expansion mechanism, you don't have the cracking, and you don't have to replace the column. So this went from a $6 million project to a few $100,000 type of project. So you can see from a cost standpoint the importance of going through this process to really understand the significance of the crack. So even though they look really bad, actually this cracking wasn't really that relevant from a structural standpoint. So the other concept, I want to go back to the introduction. We were talking about the concepts. So this concept are here, defect versus deficiency. In this particular case, these columns are classified, or this cracking is really a defect, but not a deficiency. And to illustrate that better, I can give you an example. For instance, my car. I have a car that's got all kinds of defects. It's got chips in the paint. It's got, maybe some chips on the windshield, tires a little bit worn out, but it'll still take me from A to B. So it'll still perform its intended purpose, which is provide means of transportation. So even though it has defects, it's not deficient. So that is a very important distinction here, because obviously it has impact on the cost, whether we're dealing with a conflict resolution or we're dealing with a restoration type scenario. Here's another example here, moving on to this particular one. It was actually a deficiency scenario, which you can probably see clearly on the photograph on the left, where you can see, I don't know if you can follow my cursor, but there's basically a big hole on the top of the roof. This is a one-story warehouse building that had a partial roof collapse. So I don't know if you can see there's a big hole right here on the photograph on the left. And initially, there was a study done by a firm that basically attributed the failure to deflection of the framing on the roof. And the framing consisted of open web steel joist. And they basically attributed that there was ponding due to rain, the joist deflected, and it caused the failure. But it turns out that when we did the investigation, we found that this was a pre-existing condition. It turns out that this building had a design deficiency, which was actually allowed by the building code at the time that this structure was built. So you can see the photograph here on the left. It shows a beam that is going over a very slender column. You can see the red arrow kind of pointing at the beam. You can see that being kind of folded completely. And the reason why it's folded because it had no lateral stability. And it, as I mentioned, it was allowed by the code, but it's called a instability condition. You can see the figure on the right, which is taken straight out of the code. And the code didn't change until 1989 because there were some well-documented failures of buildings with this type of framing. So there could be buildings out there now that have this type of deficient condition. So the real cause or the root cause of this particular problem was not the ponding. It was really the lack of lateral stability for the framing at the beam column connections. And there are ways to repair it. I don't want to dive too much into the details of repair, but there are ways that it can be repaired by adding bracing essentially to the top of the column by either having web stiffeners or extending the bottom core of the open web steel joist. So in this particular case, our forensic investigation allowed the owner to effectively, well, in this particular case, it was an insurance claim, and it allowed our client to come up with a conflict resolution that was favorable to the client. Now, that was the first part of the presentation, kind of an introduction about some of the terms, and I try to illustrate the concept with a couple of examples. Now, let's talk about the investigation process. So the investigation process, there's basically two methods. There is the deductive method and the inductive method. So we're getting a little bit more technical here, but I think it's important to kind of understand big picture of how we think in terms of forensics engineers go about their business. So the deductive method is kind of a top-down approach where we start out with a theory when we see the condition, and then we start making observation, establish a pattern, and develop the tentative hypothesis to see which one proves the theory. So let me give you an example. This particular photograph here shows a precast concrete double T element in a parking structure that is close to a support condition. And when you see that diagonal white crack there, so you see a diagonal crack kind of close to a support. So typically when you see a crack close to a support, it's generally due to a shear type of deficiency or behavior. But after we looked at this and started doing more investigation, it turns out that this particular element was hit by a vehicle. And the type of failure here was actually torsion. And the pattern of the crack actually went diagonal on one side, and on the other side was vertical, which is more of a pattern or torsion. So in this particular case, the pattern of the failure didn't really match the initial theory, but after performing the investigation, then we were able to come up with the right conclusion. The other method is called the inductive method, which is a more logical approach, bottom-up type of approach, where you start out by making observations, establishing pattern. You have a couple of hypotheses, and then develop your theory based on that. This is an example of a concrete floor deck that cast-in-place concrete, conventional steel reinforced. It had a lot of crack near the columns, And that's what you can see here on this figure. This is a drawing that shows the floor plan, and the circles are the kind of the column locations, and then the squares around the circles is basically what's called a drop slab. And what's happening, you have all this cracking going on. And what we did is we mapped out the cracks on the top side of the deck and on the bottom side just to see the correlation between the two. We also did some ground penetrating radar testing to estimate location and spacing of steel reinforcement, which you see photographed on the left. You can see the column here going up. You can see the floor deck. And the lines in that magenta pinkish color there is the location of the steel bars that were identified with the GPR testing. And the blue lines are showing the location of the cracks. I don't know if you can barely see maybe some of the numbers here that show the width of some of these cracks. And then the photograph on the right is a close-up of the cracks. We can see that there's a lot of debris in the cracks, and the edges of the cracks were rounded. So typically, there's a couple of scenarios that could be going on. When you see radar cracking around a column on a concrete structure like this, it could be punch and shear. However, punch and shear is a very sudden failure, and the cracks are very sharp. In this particular case, it didn't fit that pattern. Also, the cracking was through thickness, which is an evidence or is typically related to restraint to thermal movement. So in this particular case, this cracking was not a structural problem because the punch and shear is a significant structural issue, and it could cost a significant amount of money to address it. So in this particular case, it's just a restraint to thermal movement, which is very inexpensive to fix by routing and sealing the cracks. So with that, I'm going to turn it over to Charles, who is going to go over some case studies to dive a little bit more into some of these concepts. Charles?
All right, so I'm going to cover a couple of case studies to highlight the inductive method that Al mentioned. The first one is a case study about two parking garages located in the Austin, Texas area. These two garages were pretty much identical in their construction date, methodology, and essentially the drawings are the same. And both of them suffered from cracking that was observed in the spandrel beams on the perimeter of the garage. As you can see in the photo on the left, you see the diagonal cracking, and the spandrel beam is shown in cross section in the photo on the right. And what you can see, just to give you a little bit more context on what exactly that is a spandrel panel is generally a load-bearing one, is generally a girder that's on the outside of a structure that supports the framing. So it takes a lot of load, and you can see highlighted in red the load-bearing spandrel that in this case is supporting some precast double T's. So that's really the members that we're talking about here, and that are shown in cross section as you can see in the photo on the right. And so what we observed was diagonal cracking near the support. Here's a couple more photos of that. And following the inductive method, so the observation is that we have cracking in the structure. The pattern that we see is diagonal cracking near the supports, and what that leads to is our tentative hypotheses that this could be, as Al mentioned earlier, diagonal cracking near support. It's often shear and or torsion induced cracking, but it could also be a material deficiency. So those are a couple of hypotheses, and the theories supporting that are, okay, well, if it's a load-induced crack, such as from shear torsion, maybe the structure was overloaded, or maybe another possibility is the original construction could have been deficient. Maybe the reinforcing steel put into the member didn't match what was shown on the drawings. Maybe there was a material deficiency. Another option could be that the original design could have been deficient. Maybe it was never designed to meet the anticipated loads it would see in service following the building code that it was designed to. And so evaluating these theories one at a time, first, was the structure overloaded? And so the observation is that the cracking that we saw was systemic in both garages. It really occurred everywhere. And really, overloading events are often isolated to specific portions of a structure. One job I had was where we had a concrete truck, drove a fully loaded concrete truck, drive on top of a parking deck and punch a hole through the deck. So similar to that, these things usually don't occur everywhere if it's an overloading event. And based on our observations, we feel that while it is possible, it's really unlikely that that was going to be the cause of the cracking that was observed throughout both structures. Evaluating the next option or theory is that, well, maybe the construction was deficient. In other words, the spandrel beams were not built per the original construction documents, the drawings, the specifications. And that could have been improper reinforcement size and or spacing, or even a material deficiency. So in this case, ground penetrating radar was used to identify the as-built locations of stirrups in the spandrel beam. And what a stirrup is, just to give you a little bit of context, is if you look at the cross section on the right, you'll see the steel bar that runs along the perimeter of the section. That's referred to as a stirrup, and the black dots are the longitudinal reinforcement. So what we're looking at is the stirrup in that photo where we're doing the GPR. And what we found was the spacing was generally compliant with the drawings, and as is shown in the table to the bottom left of the screen, the specified stirrup spacing at the critical section near the support was 9 inches in the drawings, and we measured the as-built spacing to be generally between 8 and 9, where the smaller spacing is generally stronger and larger spacing is generally weak. So the as-built condition was slightly better than what was called for in the original drawings. Another theory was that, well, maybe there were improper materials used that could have caused cracking. Maybe there was a delayed entering formation due to steam curing, or maybe there was alkali silica reaction to a highly alkaline cement used in combination with a reactive aggregate. So concrete cores were removed from certain parts of the structure, and you can see an example of this in the photos. This core was taken from the hole that you see on the left, and the cracking at all instances where it was sampled was full depth cracking. We had those cores shipped off to a petrographer who performed a petrographic investigation per the applicable ASTM standard, which is C856. And the petrographer's conclusion was that there was no evidence showing that the cracking was due to early age material related mechanisms or long-term durability related mechanisms. In other words, it was a very strong likelihood that this crack was a load-induced crack. So moving to our next theory, was the original design deficient? So what we did was perform structural analyses on the original design to see if they met the code in use at the time. And what we found was that the original design was deficient for the combined shear and torsion loading. In other words, it had an inadequate spacing of the stirrups. And what would have had to happen is they would have had a much tighter spacing. So if you see in the bottom left hand side is a table which shows the required stirrup spacing based on the structural analysis that was performed, and on the column on the right, the spacing of the stirrups in the original drawings at the critical section. And of note is the highlighted beam label B1, where the required stirrup spacing is just a little bit more than half of what was actually provided. And unfortunately for the owner, this beam occurred at 47 locations throughout the garage. And so there was a significant design deficiency that was very prevalent throughout the structure. And really the value that we bring in the identification of this cause of this cracking is that, one, we're able to identify the cause of the cracking, but two, by identifying that, it allows the structures to be repaired prior to further deterioration occurring from maybe a durability issue with the cracks or even a collapse. So the value is really finding this issue early on before something worse could have happened, that in the worst scenario, somebody gets hurt and inevitably litigation would follow. The second case study is a garage in the Houston, Texas area that you can see in the photo on the right. It's an 11-story garage. This photo was taken during construction. We got called out because construction was stopped due to concerns with the structure that, they had seen some distress that worried them enough to where they didn't want people in the building for fear of a collapse. And what was observed when we went into the field was the cracking in this corbel that you can see here. And it wasn't just this corbel, it was actually a number of corbels. And a little bit about what a corbel is. A corbel is part of a column that's used to transmit load into the column. In this case, the column supports an inverted T-beam, which supports the horizontal framing. And so there's a lot of load coming through this connection and then down into the column to the foundations. So the observation, similar to the first one, was there's cracking in the structure. The pattern was that the cracking was occurring on the face of the corbels, and so our tentative hypotheses were, maybe it was a design deficiency, and what we did was we checked the original design and found it to be adequate. Maybe there was a material deficiency, which we generally ruled out because this problem occurred during construction, and a lot of issues like ASR, DF tend to occur later in the structure's life, which left the third option, hypotheses, maybe it was a construction deficiency. And so I'd like to take this time to talk about stress concentrations. So concrete surfaces are inherently rough, and bearing pads are used to distribute concentrated loads over a bearing area. And to simplify that, you can think of an analogy for those of you with kids. You've probably at some point in your life stepped on a Lego, which hurts really bad if you don't have shoes on, because that Lego is providing a concentrated load into your foot. However, if you're to wear a shoe, the rubber soles distribute that load over a larger area on your foot and it doesn't hurt as bad. And so the corollary being that in concrete structures, precast concrete structures in particular, bearing pads are used to distribute concentrated loads over the full bearing area to avoid stress concentrations. And here's an image showing what a bearing pad would look like in a structure, and it's represented by the black box there that's supporting a concrete member on an L-shaped beam. So that load from the beam is transferred to the L-shaped girder through the bearing pad, which makes it a nice uniform distribution of stress. And so when we come back to this garage to try and identify the causation, what we see is that the plates on which the bearing pad bear, they were actually recessed within the concrete member. And if you see on the photo on the right, there's a red arrow that shows you can see a concrete projection above the surface of the bearing plate. And what that means is that the load was not traveling as intended from the inverted T through the bearing pad into the column, but rather it was all going through this small projections of concrete above the surface of the bearing plate, which leads to a stress concentration and ultimately the cracking that was observed in many locations through the garage. And so the solution to this was, well, let's go put a temporary column in, which is effectively shoring, and we'll repair the spalls while construction can continue, and where possible, we'll grind the projecting concrete from around the bearing plates. And so the value that we bring in this type of scenario is that when we got to the job, the construction was halted due to fear of collapse. And as you can imagine, stopping a construction project for a long period of time can result in lots of damages that will come up in litigation. And by quickly identifying the cause, following by adding temporary supports, in this case shoring, we were able to allow the construction to continue while the repairs were made. So in summary, forensic engineers identify the cause of damage to a structure. And in doing so, we can help determine the different parties' responsibility for the corrective actions that are required to restore that structure. And we can also assist in determining what the appropriate corrective actions are. We're uniquely qualified as forensic engineers because we provide these architectural and structural problem-solving services on a daily basis. So it's something that we do day in and day out. And so getting a forensic engineer to look at something can ensure that the corrective action recommended is correct and the cause is properly identified. And so the value that we ultimately bring is by mitigating damages and by determining cause in an efficient manner based on our unique education and experience. And with that, I'll open it up to some questions. As Becky mentioned earlier in the presentation, please use the Ask a Question interface. And if for whatever reason you're thinking later tonight, oh, I should have asked this, well, our contact information is shown on the screen. So feel free to jot that down and reach out if there's anything that we can help with. And with that, I'll open it up to questions.
I'll go ahead and start with a question to sort of get us going here. Al or Charles, did the cracking occur only on the columns or other structural members?
I'll take that one, Charles. I think this question refers to the slide where I was showing the columns that were cracked in that precast garage. If you can go back to that one. So essentially, this cracking really only occur on the columns of the garage, and then this parking structure also had architectural columns just for decorative, for architectural purposes. Those didn't have any cracking at all. So really, it was only the load-bearing columns that had this type of issue.
And Al, why was it that only the columns were affected?
Well, my theory on that was that, precast concrete structures, all the elements are built essentially at a precast concrete plant. Then they are transported to the site and they're kind of put together like a Tinker toy. So the load-bearing columns are part of the critical path in the schedule. And these expansion mechanisms that are causing this type of cracking, particularly DEF, they occur when the columns are cured rapidly, such that the ethylene guides that are part of the cement clinker, they don't get fully consumed during the hydration process, during the curing process. So my theory is that because these columns were part of the critical path on the schedule, the precaster was trying to get them out of the precast plant as fast as possible. So they used steam curing to accelerate the curing process. But what that did is that introduced this DEF type of expansion mechanism that actually occurs later on in the life of the structure in the presence of moisture. So that's my theory. We never had the precaster information to know exactly, but that's my theory on that.
All right, I have another question for either Al or Charles. When I look back at that warehouse picture, it was pretty dramatic to me because there was only one section of the roof that collapsed. So why was it a partial collapse versus the whole thing?
Well, I'll take this one, Charles Lewis. It was a project that I worked on. This instability condition of this column was actually present throughout the entire structure. A possible reason why it only occurred in one area was because this was the area adjacent to another building, and there was more ponding during the rain event in that area. So that ponding probably exacerbated the process, but I think the ponding was a secondary issue. I think if this joist and these columns were properly braced, the structure wouldn't have failed. But I think the reason why it was partially only in this area is because that was the area that was exposed to more ponding during the rain event that might have exacerbated the problem. But the deficiency was actually present all the way throughout the structure.
Great. Well, not great for the structure, but thank you for that explanation.
Sure.
I don't see any other questions coming in. And then I have one more question. Is the corbel cracking common in precast parking structures? Is that something you see quite a bit?
Sure, I can take this one out. And I guess the short answer is no, not really, especially if it's a properly built garage. It's something we do come across, but there's usually a construction defect or a design defect that leads to it. So in properly built garages, it's seldom seen, but it does occur.
Great. Is full-scale structural modeling of buildings typical in forensics investigations?
I can take this one out. It depends on the problem. Every job is really unique. So in some jobs, depending on the behavior that we're trying to understand, yes, we would do a full-scale structural model. So the answer is it really depends. I've done full-scale structural models for many jobs in the forensic side, but I would say it's probably a fraction of the total. Maybe 10% of the jobs would I ever end up modeling the full structure. So it really just depends on the stress that's identified, the distress type. I don't know, Al, do you want to add to that at all?
Sure. Well, I mean, I think sometimes on the legal case, if you're trying to show graphically how the behavior of the structure, sometimes it can help, particularly to show in a scenario where non-technical folks are trying to understand what's going on, non-engineers basically. You're trying to show to a jury or something like that. I think having a graphical model, and now certainly there is a computer model that we develop more for the structural analysis standpoint. But there's also a model that can be built to kind of show the behavior graphically. So I think it could be used but again, as Charles pointed out, it depends on the particular project. But it's not uncommon to see, computer models built on forensics cases.
What skills should a new structural engineering graduate student focus on to pursue a career in forensic structural engineering?
Charles, you've been in school more recently than I have, so maybe you can take a stab at that.
Sure. So there's a couple of different paths, I guess, into forensics. My approach was to start with new design and really get a good understanding of the fundamentals of how structures are put together. And that's really what it comes back to, is the basics, P over A plus MC over I guess, for lack of a better way to say it. But getting that new design experience helps you understand how things oftentimes get built in the real world, especially if it's coupled with a lot of field time. Maybe, going and observing construction as it takes place, being the on-site field representative or field engineer. And then once you have that background, that good understanding, then that really well positions you to be able to decide whether or not, a design was done correctly or incorrectly. So that helps to identify design issues. And then really, if you want to focus on things, it would be, just getting the fundamentals. If there's opportunities for doing non-destructive testing type work, it's a real common tool in our trade is non-destructive testing, whether it's testing chlorides in concrete, ground penetrating radar, half cell potential, and an array of others. So getting trained in those non-destructive techniques is also very valuable. Al, I'm sure you can probably add something to that. That's kind of how I got into it, is I started new design and did that until I felt like I knew it pretty good, and then made the switch. But
yeah, I mean, my path was a little bit different. I've been involved in forensics and restoration my entire career. When you're in school, they don't, really train you for this field. I actually didn't know in school even what a photographer was. But the nice thing about this field is the dynamics of it. Every day is different. Sometimes you might be in the field on a swing stage looking at the outside of a building. Sometimes you might be at the office wearing a suit like I'm wearing now, or doing a presentation. It varies. And the way to get in it, in my mind, is basically try to understand, how structures work. Try to understand the reason for it, the behavior, really try to emphasize that, and also get an understanding of the materials component, because a lot of times the emphasis in our schoolwork is mostly on the structural behavior, but there's also a materials component. And the other part of it that they don't tell you in school is the people side of it. It's a more entrepreneurial type of business. When you start getting into this field, it is important because most of us, we go out there and we not only do the work, but also have to go out there and win our own work. So there's the ability to be able to connect with clients, and the people side of it, it's important as well in this field.
All right, with that, I think we're done. We don't have any more questions. So this is the official end of the webinar. Thank you to everyone for joining. And on behalf of Al and Charles, have a good day.
Thank you.